Hi, I'm Eileen Fowler, and I'm going to be discussing natural history research in this module. I'm going to also be discussing a multi-site study with the focus being the biomechanical analysis of gait. And this study is performed at UC Davis and at Portland Shriners as well as UCLA. So in research, we often want to look for changes that occur with age. So there's different ways of doing this. The simplest way to do it is a cross-sectional analysis. So that's the top picture here where we see there's boys of different ages. And so we would bring each of these boys in and do measurements and then plot the change in measurement as a function of age using different participants. So that gives you general information. But in a natural history study, what you want to do is look at longitudinal data, and that's the bottom slide, where we're looking at changes in individual participants over time. So that obviously is a more laborious task, as we need to bring the same child back in multiple times to gather that information. So this study that we did was a prospective longitudinal study of boys with Duchenne muscular dystrophy. And we had 85 boys enrolled. The youngest was 4 years of age. And we did 2 assessments every year. So we're interested in how our outcome measures changed over time. And outcome measures are critical to get FDA approval for new drugs. So we want to make sure that our outcome measures are sensitive to change over time, or they're actually, or sometimes we want to look for ones that are stable, depending on what the question is. Most clinical trials use simple clinical tests, such as time tests. Factors that can affect disease progression are age, weight, genetics, and environment. And also steroids hopefully will delay some of the progression of Duchenne muscular dystrophy. So these are all factors we need to consider in our studies. I've shown you this slide before. This is looking at outcome measures using the classification developed by the World Health Organization, where we look at body function and structures, activity level, participation level, and personal and environmental factors. So we had outcome measures across all of these different levels. But our primary goal of a natural history study, what made our study was unique, is that we wanted to look at biomechanical changes in gait. We wanted to know, were biomechanics clinically meaningful metrics for therapeutic trials? And were they more sensitive to change than current outcome measures? As I told you, were fairly simple. And we also wanted to know, could we observe a change in 4 to 7-year-olds? Because they're often improving in function using these other more simple outcome measures. And functional loss doesn't typically begin until around 7 or 8 years of age. So here's one of the simple tests that we talked about at the activity level, the 10-meter walk-run test, where we have a child in the hallway and we say ready, set, go, and we have them run or walk as fast as they can till they cross the finish line, which is 10-meter distance, and we record that time. And it's standard clinical test that's used for some of the clinical trials we're involved with. And we found that it's predictive for walking cessation. So if a child can do this in less than 6 seconds, then typically they're going to walk for about 2 more years at least. If they can do it, if it takes them more than 12 seconds, then it predicts that they're going to be using a wheelchair within a year. And as I said before, children at young ages, between 4 and 7, typically improve in many functional measures, and this is one where we see that they do improve. So here we have a slide of this outcome measure across age, and it's for 6 boys with Duchenne muscular dystrophy. And there's color coding here for whether the boy was taking steroids or not, and if they were taking steroids, were they taking prednisone or deflazacort. And you see that each boy is plotted, and if we look at it from 4 to 8, we really don't see very much change. But at about 8 years old, we see a divergence where all the boys start to slow down. It takes them longer to complete this test. So this really doesn't seem to be a very good outcome measure for boys who are younger than 8 years of age. So this is a setup for biomechanical analysis of gait. There is a boy with Duchenne muscular dystrophy, and we have all of these shiny balls on his anatomy, and we're going to have him walk back and forth on a walkway in our laboratory, and we have 8 cameras that are all capturing the movement of these balls. And from this, we call it three-dimensional gait analysis. It's a common way that we use to measure cerebral palsy and other kinds of movement problems. Gait laboratories, though, are expensive, so it's a lot more expensive than a stopwatch would be. They are more common in large pediatric hospitals. But we have experienced researchers and therapists and engineers that collect this data, so it is very precise. So when we talk about gait and Duchenne muscular dystrophy, as you've heard before, the boys have proximal weakness, and their ankle and their trunk postures can move the body's center of mass around, and in this way they can compensate for weakness at the hip joint during walking, because that's one of the more proximal joints that is affected. So we see toe walking, we also see lumbar lordosis. So when we watch this boy, we're going to see him walking at 9 years of age, and then we're going to see him walking at 12 years of age to look at progression. So at 9, we can see that his foot is not hitting with a heel strike, but it's more of a foot flap position. So that is an abnormality. And we see a little bit of curve in his back. But when we look at the same child at 12 years, we can see that he's really toe walking a lot now, that we don't even see the heel touching the floor, and you can really see that sway in his back, or the lumbar lordosis. And by doing this, this compensation is at the ankle and the trunk, he's moving the line of gravity in back of the hip in front of the knee, and that's decreasing the need for muscle strength at these joints. And I'm going to show you some of these ground reaction force vectors in subsequent slides. So this is the same data, the same boy, and now we're looking at the anatomical model. And you're going to be seeing some ground reaction force vectors coming up from the floor. And that's because we have force plates that are embedded in the walkway, and the child doesn't know this, but he's walking over these force plates. And if he gets a nice clean hit, we consider that a good trial, and we can use this information to calculate the strength that's required by the joints or joint moments that I'll be talking about in subsequent slides as well. So here he is, and we can see that in the top one, when he's younger, as the right foot hits the floor, that ground reaction force vector was in front of the hip. See that again, it's either through the hip or in front of the hip. But when you look at the lower slide, as he's older, it is really going through the hip or in back of the hip as he weight bears. So the specific outcome measures that we can calculate using gait analysis are joint kinematics, which are the angle between the segments. So we can calculate the knee joint angle, the hip joint angle, the ankle joint angle, and then also joint kinetics, which include these moments, and they require the ground reaction force vectors and the motion data. And I'm not going to have you remember this busy slide, but it's biomechanics, there's math involved, and for this model, you can see that we could, here we're looking at the angle between these two segments, and also this ground reaction force vectors that are affecting this distal segment. So we calculate for the distal segment and work our way up to finally calculate a joint moment about the hip. So this is what we would see in normal movement. And when we look at the figure above the data, the black limb is the limb that we're focusing on in the data. And the way that the data are plotted is from initial contact of the right foot with the floor to the next initial contact. So we have a stance phase here where the foot is on the floor, and then a swing phase where the foot is off the floor. And then this is our normal range that we see, and we're interested in the peak moment that we find after initial contact, and that's a peak extensor moment. And then also this is the flexor moment. And 0 means that the ground reaction force vector is going right through the joint. So if we look up here at this arrow, this is the ground reaction force vector. This is the joint center of the hip. So, and this distance between is the lever arm. So if there weren't any hip extensor muscles working here, the trunk would fall forward. But in a static sense, if this was a static analysis, the force times this distance would give you the joint moment. Now, as the gait progresses and the ground reaction force vector goes through the joint, then there's no moment, as you can see right here, it goes to 0. And then if it goes back, we would see a flexor moment at the end of stance, which occurs here. So now, if we look at these moments for our young boy that we showed you with Duchenne muscular dystrophy, we're going to compare that to normal. So here is our normal gait, and the vector, this picture that I'm showing you is right about this phase. We're looking at peak moment. And you can see here for peak moment that the ground reaction force vector is in front of the hip, and that moment is within normal limits. And the duration of that moment during gait is also normal at this point. So when we look at when he's 9 years old, we can see that it's closer to the hip joint than would be normally, and we see a reduced peak hip extensor moment and also a reduced duration of the moment. When he's 12, we see that the ground reaction force vector is going through the joint almost immediately after weight bearing, and that the duration is very short. So we see increased compensations due to weakness as the child becomes older. So now that was in a boy who progressed from being 9 years to 12 years. We wanted to know, were these joint moments below normal in young boys 4 to 7? And also, what if they had a treatment? So boys tend to receive steroids for the first time between the ages of 4 and 7. So we wanted to know, if we just looked at naturally when the boy went on steroids, would we see an increase in hip joint moments with treatment? So our study design was that we had 2 groups of boys in this age group, and we had a control group that had not yet gone on steroids, and a group of boys who we measured before and after the onset of steroid treatment. So this is our control group. There's 9 boys, and you can see that first of all, if we look at just the angle, the motion that we see here, if you look compared to this normal band, it's pretty close to the normal band. The dotted line is baseline, the first time we collected data, and then the solid line is a year later. And we can see that there really isn't much change when we look at this. Now, if we look at the moment, however, we can see that already at this age group, the peak moment is markedly reduced, and that it decreases further a year later. So it progresses over time. And the duration of the moment also is reduced over time. Now when we look at the steroid treatment group, again, we do not see very much difference in the motion just by looking at the child. But when we look at the joint moment, we see that it is reduced at baseline, but now with steroid treatment, it moves up, it increases, and it's now within normal limits. And also the duration, which was reduced initially at baseline, a year later with steroid treatment is now within normal limits. So we did see a significant improvement for the peak moment here. Now when we do a statistical comparison between the 2 groups, if we look at the change here for the control group, for both the duration and magnitude of the hip moment, and we compare that to the change for the treatment group, we did find a significant difference between the 2 groups. So in summary, natural history studies describe the change in outcome measures over time to help design clinical trials. We need valid and reliable measurements that are sensitive to change. Decreased hip moments are reflective of proximal weakness, And they are early markers of disease progression because we do see them in these young children. And we also found that they're sensitive to change because hip joint movements improved with steroid initiation. So now I have a few review questions for you. The first one is gait analysis at the body function and structure, activity, or participation level of the ICF. The second is, do children with DMD between 4 to 7 years gain or lose function? And this is with the typical timed functional measures. How does steroids treatment alter the natural history of boys with Duchenne muscular dystrophy? So that concludes this section, and thank you for your attention.